All right, so now we're going to talk about the limit laws, and really the limit laws are exactly the same as the limit laws are for one variable x. The only difference is instead of x approaching some value a, now it's going to be xy approaching some value at ab. So the constant law works. You can just pull a constant out. The limit of a constant is going to be just the constant. If you take the limits of x at AB, we're only evaluating the x parts here, so that's why you get A. Similarly, the limit of x, y going to AB of y just goes to B. That's similar to the identity laws from actual limits. The sum of the limits is the limit of the sum, or vice versa. The difference of the limits is the limits of the difference. So again, you can do these in any order, doesn't matter. You can take the limit of f of x first and then g of x and add them together, or you can add the negative if you want to do subtraction. You can pull out a constant. If you've got a constant c, we just pull that constant right out. The product of the limits is just the limit of the products. And similarly, the quotient rule works the same way, provided that your m doesn't equal 0. And the power and root laws work the same way. If you take the limit of something raised to a power n or the root n, it's going to be whatever that limit is raised to that root or power. Now, let's give these two problems a try. All right, so first problem here, number 63, we're going to try to evaluate the limits if they exist. Let's try to use these limit laws. I mean, this should be pretty clear as what we're going to do with this, but we can use the quotient rule first, or the quotient limit law. So this equals the limit as xy approaches 0, 0 of our numerator all over, same limit here, okay, and then we can break these down further because now we have sum and differences here. And I can, let's see. That would be the first one, and then we've got limit that's our numerator, and our denominator also has 3 parts. Excuse me, that's minus, not plus. So 10y squared. And our constant here is 6. All right, so now this changes. So we're only evaluating the x values at the x component and only evaluating the y at the y component. So that gives us limit as x approaches 0 of 4x squared plus limit as y approaches 0 of 10y squared. And the limit of this 4 is just 4, so plus 4. That's our constant rule there. So I've evaluated the limit of that piece. And similar with the denominator, we've got an x That's subtraction, I'm sorry. And again, 6 evaluated anywhere is still going to be 6. So ultimately, this is going to equal 4 over 6. As we plug in 0 for either the x squared or the y squared, it goes to 0. So we have 4/6 or 2/3 or whatever. And again, all that work wasn't really necessary for this problem. At this point, we could substitute in the 0, 0, and it would turn into 4 over 6. But that's how we use the limit laws. 65 is going to involve a little bit more. So we'll do the same sort of thing. Oh, excuse me. This will be fine. That's going to what, 0, 1? That's all over this limit. Well, I'm jumping ahead. I'm sorry. Okay, and actually I'm going to change colors here so as to not confuse our next question with it. All right, so this is going to equal the limit as y approaches 1 of y squared. And then we've got a sine of x over x, so I can take this out, and that's going to be multiplied by the limit as x approaches 0 of sine x over x, which if we substitute in the 0, we get a 0 over 0. We can solve that with a squeeze theorem. You probably did some of that in Calc 1, but at that point, you would not have had L'Hopital's rule, which we do have. So the limit of this first bit is just 1 squared, and this part will be the same as the limit as x approaches 0 of the derivative of sine of x, which is cosine of x, over the derivative of x, which is 1. And this is L'Hopital's rule. So L'Hopital's rule. That's what we did there. And then evaluating at 0, cosine of 0 is 1. So that's just going to equal 1 times 1, which is 1.